Welcome back. So just to review what I was doing in the last video before I run out of time, I said that, okay, conservation of energy tells us that the work I put into the system, or the energy that I put into the system, because they're really the same thing, is equal to the work that I get out of the system, or the energy that I got out of the system, right? And I said, well, that means that the input work is equal to the output work, or that the input force times the input distance is equal to the output force times the output distance. That's just the definition of work. And let me just rewrite this equation here. If I could just rewrite this exact equation, I could say, so the input force, and let me just divide it by, just for kicks, let me divide it by this area. Because what I'm talking, the input here, I'm pressing down this piston that's pressing down on this area of water. So it's input force, and let me say that times the input area. Well, let me call this input. Let's call it the input 1. And let's call the output 2 for simplicity. So there's going to be some, let's say I have a piston on the top here. Let me do this in a good color, like brown. Brown is a good color. So I have another piston here, right? And there's going to be some outward force, F2. And this is the general notion is that I'm pushing on this water. The water can't be compressed, so the water is going to push up on this end, right? So the input force times the input distance is going to be equal to the output force times the output distance, right? This is just law of conservation of energy and everything we did with work, etc. So I just I'm rewriting this equation. So if I take the input force and divide by the input area, let me just switch back to green. And then let's say I multiply by the area then. And then I just multiply times d1. You see what I did here? I just multiplied and divide by a1, which you can do. You can multiply and divide by any number, right? These two cancel out, is equal to the same thing on the other side. F2, I'm not good at managing my space on my whiteboard. F2 over A2 times A2 times D2. Hopefully that makes sense. So what's this quantity right here? This F1 divided by A1. Well, force divided by area, if you haven't been familiar with it already, and actually if you're just watching my videos, there's no reason for you to be, is defined as pressure. Pressure is force in a given area. So this is pressure. So we'll call this the pressure that I'm inputting into the system. Pressure 1 times, and what's area 1 times distance 1? So that's the area of the tube at this point, the cross-sectional area times its distance. Well, that's equal to this volume that I calculated in the previous video, right? We could say that's the input volume, or V1. Pressure times V1 is equal to the output pressure, right? Force 2 divided by area 2, right? That's the output pressure that the water is exerting on this piston. So that's the output pressure, P2. And what's area 2 times D2? So this area, the cross-sectional area, times the height at which how much the water is being displaced upward, that is equal to volume 2, right? But what do we know about these two volumes? And I went over it probably redundantly in the previous video, is that those two volumes are equal, right? V1 is equal to V2. So we could just divide both sides by that equation, and you get the pressure input is equal to the pressure output. So P1 is equal to P2. So P1 is equal to P2 coming out. P2. And I did all of that just to show you that this isn't a new concept. This is just the conservation of energy. The only new thing I did is I divided, we have this notion of the cross-sectional area, and we have this notion of pressure. So where does that help us? Well, this actually tells us, and you can do this example in multiple situations, but I like to think of it if we didn't have gravity first, because gravity tends to confuse things, but we'll introduce gravity in a video or two, is that when you have any external a pressure onto a liquid, so onto an incompressible fluid, that pressure is distributed evenly throughout the fluid. And that's what we essentially just proved just using the law of conservation of energy and everything we know about work. And what I just said, that's called Pascal's principle. That if any external pressure is applied to a fluid, that pressure is distributed throughout the fluid equally. And another way to think about it, I mean, we proved it with this little drawing here. Another way to think about it is, let's say that I have a tube, At the end of the tube is a balloon. Let's say I'm doing this on the space shuttle. And it's saying that if I increase, so let's say that I have some piston here, right? And let's say I were to, and this is stable, right? And let me say I have water throughout this whole thing. Let's say I have water throughout the whole piston. Let me see if I can use that fill function again. Oh no, there must have been a hole in my drawing. Edit. Let me just draw the water. So I have water throughout this whole thing. And all Archimedes' principle, all Pascal's principle is telling us that if I were to apply some pressure, here, pressure in, that net pressure, so if I, and that pressure is going to, that extra pressure I'm applying is going to compress this a little bit. That extra compression is going to be distributed through the whole balloon. Let's say that this right here is rigid. Let's say that's some kind of metal structure. The rest of the balloon is going to expand uniformly. So that pressure, that increased pressure I'm doing is going through the whole thing. It's not like the balloon will get, it's not like the balloon is just going to get longer, that the pressure is just translated down here, or that, just up here the balloon's going to get wider and it's just going to stay the same length there. Hopefully that gives you a little bit of intuition. But going back to what I had drawn before, that's actually interesting because that's actually another simple, maybe or maybe not so simple machine that we've constructed. And I almost defined it as a simple machine when I initially drew it, right? Let's draw that weird thing again where, it looks like this, where I have water in it, where there's a bunch of water. Let's say, make sure I fill it so that when I do the fill, it's completely filled. It doesn't fill other things. There you go. So this is cool because this is now another simple machine. Because we know that the pressure in, is equal to the pressure out, right? Pressure in is equal to the pressure out. And pressure is just divided as force divided by area. So the force in divided by the area in is equal to the force out divided by the area out, right? So let's say, let me give you an example. Let's say that I were to apply with a pressure of, so let's say that the pressure in is equal to 10 pascals. Now that's a new word, and it's named after Pascal's principle, or Blaise Pascal. And so, and what is a Pascal? Well, that is just equal to 10 newtons per meter squared. That's all a Pascal is. It's a newton per meter squared. It's a very natural, unit. So let's say my pressure in is 10 pascals, and let's say that my input area is 2 square meters. So, if I looked at the surface of water there, it would be 2 square meters. And let's say that my output area is equal to, I don't know, 4 meters squared. So what would be so what I'm saying is I can push on a piston here, and that the water is going to push up with some piston here, right? So first of all, I told you what my input pressure is. What's my input force? Well, input pressure is equal to input force divided by input area. So 10 pascals is equal to my input force divided by my area. So I multiply both sides by 2. I get input force is equal to 20 newtons. So my question to you is, what is the output force? How much force is the system going to push upwards at this end? Well, we know that if my input pressure was 10 pascals, my output pressure would also be 10 pascals. So I also have 10 pascals is equal to my out force over my out cross-sectional area, right? So I'll have like a piston here, and it goes up like that. And so that's 4 meters. So I do 4 times 10. So I get 40 newtons is equal to my output force. So what just happened here? I inputted, so my input force is equal to 20 newtons, and my output force is equal to 40 newtons. So I just doubled my force, or essentially I had a mechanical advantage of 2. So this is an example of a simple machine. And it's a hydraulic machine. Anyway, I've just run out of time. I'll see you in the next video.